So let's think of our usual particle that is forced to live between x equals 0 and x equals L. And let's say that it's in a state such that it's equally likely to, it's in a superposition of being in the ground state and the first excited state. In other words, psi of x and t is 1 over root 2 psi 1 of x e to the minus I e1t over h bar plus psi 2 of x e to the minus I e2 t over h bar. So if we write this out in terms of the psi 1 and psi 2 expressions, we get 1 over the square root of L, because there's a square root of 2 over L here. Let's see, we have sine of pi x over L e to the minus e1t over h bar plus sine of 2 pi x over L e to the minus I e2t over h bar. And now we can consider the probability density, and we'll see how this varies with time. So let's consider psi of x and t modulo squared. This is the p, the probability density. And that looks like what? So we have, we're squaring this. So we have 1 over L times sine of pi x over L squared plus sine of 2 pi x over L squared, right? And the time dependence doesn't exist for these two terms because we have psi star psi, and that makes this term get multiplied by an e to the I, e1t over h bar, and similarly for this one. So we have those two values, and then we have cross terms, but we have two cross terms. We get a 2 sine pi x over L sine of 2 pi x over L. And as we've seen before, we have a cosine, right? The e to the I times difference in energy, t over h bar, reduces to a cosine of the energy difference, E1 minus E2, or the other way around. This is a cosine function, so it doesn't really matter, over h bar. Close that. And we can really write this as, let's rewrite this as 1 over L. For simplicity, we'll rewrite this last part. This is sine squared of pi x over L, sine squared of 2 pi x over L plus 2 sine pi x over L, sine of 2 pi x over L times the cosine of, if we go back to the ENs, we can write E1 and E2 out and realize that this is the same thing as cosine of 3 E1 T over H bar. So the energy difference is 3 times, the difference between E1 and E2 is 3 times the energy E1. So that's psi of x and t modulo squared. And so we can recognize the time dependence here. So at t equals 0, we have t equals 0, this term looks like that. That's just 1, right? So we have this term, and then we have this term, and we can plot this. So let's think of plotting this function in x, right? There's no time dependence there at t equals 0. So let's plot this psi of x and t modulus squared. Let's plot this as a function of x in time. So I guess we can use a red. So at t equals 0, what does this look like? So this second term has is a combination of two terms, one that goes from 0 to L like that, and one that goes to from 0 to L like that. And so it has, the second half is negative, and so we're multiplying something that's always positive by something that is negative on the second part of the well, and so that will produce a negative sign in this term. So we're subtracting from this on the second half of the well between L over 2 and L, and so the function ends up looking something like this. It's going to peak there, and then it comes down, and it has a smaller value in this part of the well and something like that. And so this is L, and L over 2 is somewhere over here. So that's what that looks like. So this is the, let's just put it here, t equals 0. That's the red. And now we can think of, let's see, t, choose a different color. Let's make a t equals h, so h bar over 3 E1 pi. So when t is equal to pi h bar over 3 E1, let's see, this becomes h bar over 3 1. We only have pi. You have the cosine of pi, and that brings in minus sign, and so we are shifting things such that we are adding the second term, unlike for the red curve where we subtracted it from that. So we're going to add that. And what does this look like? This ends up looking like sort of the mirror reflection of this. So we're going to see if I can do this. We're going to come over here and go up a little bit and come down somewhere there, and come up somewhere like this, such that we can reach a maximum there, and then we come back down here. Something like that. And then there is a time, let's just do it by pencil. There is a time in between these two times where the cosine goes to 0, And that time is pi h bar over 6 E1, because that makes this pi over 2, and the cosine of pi over 2 is 0. And so this whole term disappears, and we just have these two terms. But that's just a combination of one big bump that we squared, the sine of pi x over L, and the sine of 2 pi x over L, which looks like this, but we square that, so we just get a completely symmetric function about L over 2, and that's going to look like, let me try to do it like that. We're not going to come down to 0, but we will, and this is supposed to be symmetric, so we can flip these two sides and get the same function. So it's something like that. And so we can see that at t equals 0, there is a greater probability of finding the particle on the left-hand side of the well. And as time increases, we're moving from that to the dashed line for the probability density. And so the probability of finding the particle starts to increase in the middle part. And it's sort of the same here and there, representing sort of transition this way. And then at the later time, it's more likely to be found on this side of the well than on the left. And so in some sense, we're describing a particle that is moving this way. In fact, this particle is moving, the probability density can be thought of as describing a particle that's moving back and forth.